I would like to talk about, I want to just do one more example of the trigonometric substitutions like we were doing last time, and then we can go on to something a little different. In my opinion, the trigonometric integrals and the trig substitutions, to me, are some of the hardest kind of this type of tricks that we're going to do all semester, so it will not be all that stuff for the rest of the semester, fortunately. Let's try, I just want to try one more of these. Integral, sorry, my line's thick. How about x squared over square root of 16 minus x squared dx? All right. This one is very similar to the ones we were doing last time. I just wanted to try one more example and make sure it feels all right. So you have to remember which tricks to use, and the appropriate one in this case is if you see a squared, square root of a squared minus x squared in the integral, then your trig substitution that you should try should be x equals a sine theta dx equals a cosine theta d theta. Right? This is the basic idea. There's a similar one. If instead of a plus, if instead of a minus, it's a plus, you should use a tangent and a secant squared. Although those tend to be a bit more of a pain. They end up giving you integrals with secants and cosecants and whatever. Anyway, let's try this as the substitution. So I am going to plug in where I see x is a sine theta. So this is a sine theta square. And on the bottom, square root 16 minus, sorry, not a. What's a in this example? 4, yeah. So I'm going to do x equals 4 sine theta. Put a there. That means dx will be 4 cosine theta d theta. All right, so this a, I meant 4. 4 sine theta squared, and then 16 minus 4 sine theta squared down there. And then the dx becomes a, which is 4 cosine theta d theta. All right? Anyone remember this from last time? Can suggest what I should do next? You want to, simplify stuff as much as you can. Square those square things. So where it says 4 sine theta squared, you square the 4, you also square the sine theta. So this is, I'll write as 16 sine square theta over square root 16 minus, same thing in here, 16 sine squared theta. Up here, 4 cosine theta d theta. All right, what else can we do? Yeah?
You can factor up to 16 and then square 16, like to bring it out to the outside.
Yes, factor the 16 out of the square root sign and it becomes a 4. When you pull something out of a square root like that, you can factor it out, but it has to get sort of square rooted on its way out. So this is 16 sine squared theta over 4 square root 1 minus sine squared theta, and then 4 cosine theta over here. All right. Now what you got? Maybe someone I haven't heard from today. Yeah?
We cancel all the 4s.
Cancel the 4s, sure. All right. Anything else? Yeah?
You can make 1 minus sine squared theta cosine squared.
Yes. This is sort of where the money's at as far as this trick. I would say this is the whole point of doing this trick, is this becomes cosine squared theta on the bottom, and then you can sort of cancel the squaring. So square root of cosine squared on the bottom is just cosine, and in fact that's going to cancel the other cosine that you see there. But I'll write this out. 16 sine squared theta, down here cosine theta, and then over here times cosine theta d theta. These cosine thetas can cancel, and the 16 can pull out of the integral, I suppose. And now this is all we're left with. I mean, it's not going to simplify any further than that. Any ideas? How can we do this? You often will simplify as much as you can, and then you end up with just something that you have to do using one of your bag of tricks that we know already. Anyone got a suggestion for this one? Yeah?
Did you do the 1/2 thing?
The 1/2 thing, he says. Yeah, I agree. Do the 1/2 thing. So this is the old sine squared theta is 1/2 1 minus cosine 2 theta. I think everybody got it? No. All right. So do that down there. So this is 16 integral of that stuff. 1/2 1 minus cosine 2 theta. Oh. D theta. Did everybody get the list here? Okay, I'm starting to feel okay about this one. Any suggestions to finish it off? It's getting there. Can I do something with this 1/2? Yeah, I would say actually there's two things that occur to me. You could distribute the 1/2 across these two things, or you could move it outside the integral. I think that's actually a little easier. If I just take the 1/2 outside the integral, it's going to be an 8 out there. 1 minus cosine 2 theta. Great. And now I think we can just do this integral. There's two parts there. Everybody get one of these papers? Oh. Two parts. The 1 becomes theta, so it's 8 out here. The 1 becomes theta minus cosine 2 theta. This is one of those other things, generally speaking. Cosine of k theta is 1 over k sine of k theta, right? So that's what we're going to do for the other part. Cosine 2 theta becomes 1 over 2 cosine 2 theta. All right. Now did everybody get one?
Doesn't it become sine?
Yeah.
Sine, yeah, that's what I wrote over there. Thanks. Not cosine in there. When you do the integral, it becomes sine. Great. All right. And then one last step, replace the theta with x. And this is a little complicated because our original substitution, remember, was x equals 4 sine theta, right? Refresh my memory. Yeah, 4 sine theta. And so, can anyone say what is theta going to be then in terms of x? You have to rearrange a little bit. Yeah.
Inverse sine of x over 4.
Yeah, excellent. Inverse sine of x over 4. Great. Divide the 4 over and then do the inverse sine on both sides. All right. So my final answer shall be 8. Theta, no, not theta. Inverse sine x over 4 minus 1/2 sine of 2 times inverse sine x over 4. There you go, plus c. All right. This is sort of strange looking answer. Can you do anything with this? Sine of 2 sine inverse? Answer is no. If the sine was right next to the sine inverse, then they would just sort of cancel each other out. But that 2 in there really screws it up. Anybody feel like, can I just take this 2 out front? The answer is absolutely not. You definitely can't do that. Like it is just straight up not true. Can you do? Is this just true? Can you just pull a 2 through a sine? Of course not. No. Don't do that. You cannot do everything in red is wrong. I'm just going to erase it all. You just got to leave it like that. All right. Excellent. Any further things to say? This one was maybe a little easier than the last one we did last time. I don't know. These are all a little involved, I think. You'll get some practice with these on the homework for next week. All right. Great. Let's move on to something different then, and in my opinion, quite a bit easier. Although still, there's some steps to do. But this is the last of our bunch of what you might call techniques of integration. These are what we've been doing for the past little while. Is different kinds of tricks for doing integrals. They are, the U substitution is the most basic one, and then we did the integration by parts, and then various trigonometric integral tricks, and then these trig substitution tricks. The last kind of trick, and this is one that maybe some of you have seen before. The last of these integral tricks is integration by partial fractions. I kind of like the partial fractions. Partial fractions. It is a cute little trick. Yes?
On the quiz, will you say, solve this problem using trig substitutions, or will it just be the problem?
I will not say that, but the numbers of the questions always correspond exactly to the number on the checklist. So you will know which is which for that reason. Yeah. And actually I don't know if you care about this, but this is one thing that I don't like about having the grades based on this list, is that there's no opportunity for me to put a problem on there where you're not sure what you're supposed to do, and then you have to figure it out for yourself. Because you can always tell based on what number question it is. A little pro tip, if you're in this class. There is never going to be a question like, here's an integral, you figure out what you're supposed to do, which of your tricks to use, and do it. Because every question is labeled according to each section. What are you going to do, right? Partial fractions. All right, this is the last of our integration tricks. And this involves doing integrals, which I have sort of a little preamble here. When you do this partial fractions tricks, so this trick often ends up with stuff like maybe you're going to end up with something that looks like this. You start with something more complicated looking than that, but then you do this partial fractions trick, and what it ends up with is like that. And there is a very simple way of finishing an integral like this. So if you really had to do these, you could do them, each of these separately, by doing two different u substitutions. And you basically just make the denominator u, and it turns into 1 over u. And then the fact that there's a 2 down here gives you an extra constant in the u substitution, but it doesn't really change much. This is a 1 over u, and so the result ends up being the natural log of u with some extra constants here and there. Now, just so that we don't have to work through these u substitutions, all these are handled by this general integration formula, which is worth remembering, at least when you're doing these partial fraction problems. It's best to just memorize this formula. So in general, when you have an integral of 1 over a linear polynomial, this only works when it's like a binomial downstairs with just an x plus another a constant with a dx. The answer is 1 over a ln absolute value ax plus b. Like I said before, if you were doing this sort of longhand, you would do a u substitution where u equals the bottom. Then the integral turns into integral of 1 over u. The integral of that is ln of u, which is why it looks like this. And the extra 1 over a comes from the constant in the u substitution, with a plus c, of course. All right, so for these problems, you should remember this basic formula. To me, there's not a lot to remember here. It's really, when you have 1 over something, you expect the answer to be the log of that thing. The only really thing to remember is this 1 over a, and that comes because of the a coefficient here. When you do the substitution, you end up with the extra 1 over a. anyway, this is the formula to finish. So for instance, if I was doing this problem, using the formula in the box, I can immediately say the answer is 1/2 ln 2x plus 1 plus, that 3 just stays as a 3 coefficient, and then 1/8 ln 8x minus 7, right? That's the using the formula in the box. This here is not the partial fractions trick. The partial fractions trick is another thing which you do first, and then you end up getting something that looks like this, and then you use the formula in the box to handle it at the very end. All right, but this is just a little preview. Just like the trig substitution trick, you do some stuff, and usually you end up with a trigonometric integral, which you have to do one of your other tricks for. All right, so let's talk about partial fractions. It is, generally speaking, used as a trick to do integrals, but it's a more basic trick. So I will say we use partial fractions in something like integral of 1/x squared minus 3x plus 4 dx. The way I'm talking about partial fractions, it's a trick for doing integrals, but actually people learn about this. Like I have a kid in high school and he is doing partial fractions even though he doesn't know what the integral is. So sometimes people learn about doing the partial fractions trick even outside of the context of doing integrals. And their teacher said something like, you should just learn this because I said so. I think they don't really talk about what the partial fraction is useful for. It's useful for doing integrals. Anyway, the idea behind the partial fractions is to take this, the idea is to write this as a sum of two fractions. That's why it's called the partial fractions. You sort of split that thing up as a sum of two fractions. And what's hard about that, of course, is that it has this denominator, and you can't just split up a denominator as a sum of two fractions. If it were in the numerator, you could easily split it up, but it's in the denominator, so that process is a little tricky. But I'll tell you, it turns out, in this case, if you know how to do it and you work it out, in this example, this 1/x squared minus 3x plus 4 actually is equal to 1/5 over x minus 4 plus 1/5 over x plus 1. And the partial fractions trick is figuring out how to do that. Because if you can do that, you rewrite the integral as this, and then you just use that ln thing for each of those, and the integral becomes easy. All right, so this makes the integral easy. So the big question when it comes to doing the partial fractions thing is, how do you actually figure this out inside the box here? This is called the partial fractions decomposition sometimes. Start with a fraction involving some kind of polynomial in the bottom and split it up as a sum of two different fractions over here with different denominators. This is the big idea. All right? Let's just try to do that example. It comes down to figuring out what are the 1/5 and the 1/5, and also what are these denominators supposed to be. Does anyone maybe able to look at this and tell where do you think these denominators came from? Yeah?
Like factor.
Yeah, these are the factors of this polynomial that we started with. And so the partial fractions is about, you start with a polynomial down here, you factor it, and then somehow split it apart into two fractions, and somehow you have to figure out that these are both supposed to be 1/5. So this is the idea here. You factor the bottom, and then these factors become the denominators of these fractions that you're looking for. These factors will be the fraction denominators. So in this example, x squared minus 3x plus 4, of course, when you factor it, you do get those two factors, x minus 4 and x plus 1, which means my two fractions, those are going to be the two denominators of my fraction. Yeah?
When I got you x squared minus 3x minus 4.
Minus 4. Yeah, did I copy this wrong? I wrote it wrong at the very beginning. Oh, this is so embarrassing. Minus 4. Yeah, I wrote it wrong on my entire paper here. Sorry about that. I do mean minus 4 instead of plus 4. He's right. Those are not the factors. Thank you. Sorry about that. All right. The real deal is, can I find these numerators, 1/5 and 1/5? How do you figure that out? And it's not so hard to do this. So we set it up like this. This is my goal. 1 over this thing is supposed to be something over x minus 4 plus another something over x plus 1, right? And our goal is to solve for a and b. I want to figure out, and if you believe what I said before, they're both going to equal 1/5, but that's not obvious why they are. But we can indeed solve for a and b. And the way to do that is, on the right-hand side here, we can actually add these fractions together with a common denominator. So we are going to make common denominator here. And actually add the fractions together. The common denominator, since, I mean, these are not numbers where you look for like the least common multiple or anything. It's just the common denominator has to be the product of those two denominators. And so when I make my common denominator, for each one, it will be x minus 4 times x plus 1. And the numerator of the first one is a times x plus 1, right? Because the way that you get this from here is you multiply here on the top and the bottom by x plus 1. So it ends up looking like this. And then similarly for the other one, to make the common denominator here, I have to multiply by x minus 4 on the top and the bottom. So the other one looks like b x minus 4 over x minus 4 x plus 1. All right, and of course this all equals, I'll write the left-hand side again, 1 over x squared minus 3x minus 4, like that. All right. I said make common denominator and add them together. So they have a common denominator now. Let's actually add them up, which involves just adding the numerators together. Maybe I'll distribute the a and the b also. So it's going to be ax plus a, and then the second one plus bx minus 4b. And all of this is over this common denominator with a 1 on the other side. All right. And now if you look at this equation all the way across, the denominators are the same now. That's because those things on the right, they really are the factors of the thing on the left. And so that means I can just sort of cancel the denominators, and what we have is just the two numerators being equal to one another. 1 equals ax plus a plus bx minus 4b. And my goal is to solve for the a and the b. Now this is to me a little worrying because I have one equation, but the two variables a and b, and I want to solve for a and b. Anybody have an idea here? How could I solve for a and b when there's only one equation here? Like, I would like to have a system of equations with two variables. Anybody done this before? Maybe. Remember how to do this step? Yeah?
Well, I know part of it involves, at least the way I did it in the past, was taking the x out and doing like an x times a plus b.
Mm-hmm. I like that. So on the left side, I'm going to write it, let's just keep it as a 1. But yeah, gather the x's together and factor the x out. So it'll say a plus b x. And then gather the constant ones together. They are a and negative 4b. Great. Okay. Now what? Maybe I will write on the left side a slightly more suggestive way. 0x plus 1. Yeah?
Do you set the a plus b equal to 0 and then the 1 equal to a minus 4b?
Yeah, that's right. So this right here is a single equation with a polynomial on either side. On the left side, there's this polynomial in x, and on the right side, there's this polynomial in x. And if those two polynomials are equal, it means they must have the same coefficient on x, and they also must have the same constant part. So the coefficient on x on the left is 0. It must equal a plus b. And also the constant part must equal this. So we equate the can I say, like, the like powers of x, right? The coefficient on x on both sides must match, and the coefficient on the constants on both sides must match. Equate the like powers of x. I don't really like the way that I wrote that. Can we just say the like terms? People say the like terms, right? Anyway, what we get is 0 equals a plus b, and also 1 equals a minus 4b. And now this looks like a more ordinary system of equations in two variables, and I can solve the system for a and b. So it's a very different kind of trick, of course, to the ones that we've been doing lately, but it's a little maybe more down to earth or something. Not terribly fancy. You just have to remember how to do it. Solve the system, and you can solve the system by any methods that you like. There's several ways to do it. You can. I usually like solving one of the equations for one of the variables and then plug that in, doing substitutions. Or if you want to be real fancy about it, you can add and subtract the equations to one another. I don't know if you like that. Anyone have a preference? No. Let's just do substitutions. So I'm going to solve the first one for b, let's say. So the first line says b equals negative a, and then I'll plug that into the other one. It will say 1 equals a minus 4 negative a, right? Simplify this business. 1 equals 5a. So a is 1/5, which I like. This is what we were expecting the answer to be. And then what's the b? The b is minus a. B is negative a, which is negative 1/5. Is that what I said all that time ago? No, I left out the minus sign. Did I? Striking out today. That should be a minus there. Sorry about that. Unless I messed this up, but I think this is correct, what I did down here. All right. This is the partial fractions trick. So just to summarize, so the whole point of this is, remember where we started? Was way up here, right? This thing equals a over x minus 4 plus b over x plus 1. So this says 1 over x squared minus 3x minus 4 is a, that was 1/5, over x minus 4 plus negative 1/5 over x plus 1. And we have completed the partial fractions decomposition. That's the whole point of the partial fractions trick. All right. And then the reason for doing this is now we know how to do the integral. So if we do the integral here, integral 1 over this business, x squared minus 3x minus 4 dx is integral of this one, 1/5 over x minus 4 plus negative 1/5 over x plus 1. And then we do the integral of each term separately. This is going to be a ln of x minus 4. This is going to be a ln of x plus 1, using what I wrote in the box from before. And these 1/5 in the numerators just end up as coefficients on my answer. So this is the integral, well, minus 1/5 ln x plus 1, like so. This is why you do the partial fractions, because it lets you do the integral better. And there are actually other settings in which the partial fractions is helpful, which is maybe why some people learn to do it in high school. But this is, for our purposes, this is the goal of the partial fractions. All right. Any questions about that? Or we can do another one. I got another one, and then I have one for you all to try. That might do us for today. Actually, there is a slightly more complicated type, so this is like an easy one that we just did, and I want to try another easy one, and then I'll have you all try one. All right, how about, let's try new example here. The integral 5x minus 16 over x squared minus 7x plus 10 dx. All right. This is my integral. So you should look at that. You might consider doing u substitution, I guess, if you don't know what kind of question this is, but the u substitution is not going to work for something so complicated. You could try picking u to be the denominator, but then the du would not appropriately match in the numerator. So we should do the partial fractions. So I'm going to just kind of like forget about the integral for a while, do the partial fractions. Partial fracs. That's how the cool kids say it. The partial fractions, all right? We are going to begin with what I started with. And then I go, this equals a over something, b over something. This is the general setup of the partial fractions. What are the denominators in this case? X minus 5, x minus 2. Yeah, I like that. Right, you factor the original denominator, and these, what you want as the denominators in your partial fractions are the factors of what you started with. All right. One thing that I kind of like about partial fractions, I don't know if you like this or not, but there's something kind of magical to me about the fact that this is even possible. Just that this is a quadratic on the bottom, but it has x's on the top. But it turns out actually no matter what you start with, you can always write this. Unless, like I said, there are some harder technical cases, but basically this trick always works. It's a little strange to me. These always end up being constants on the top. You never have to put an x on the top, even though there were x's on the top to begin with. This is what's slightly magical in my opinion. Anyway, let's continue here. So on the right-hand side, we make common denominators and add everything together. So the right-hand side, my common denominator will always involve just multiplying what you originally saw in the denominators. So the first one needs to get multiplied by x minus 2 on the top and the bottom. The second one needs to get a x minus 5 on the top and the bottom. All right, distribute the a's and the b's on top and add everything up. So I get ax minus 2a plus bx minus 5b. And on the bottom, what I always had all along on the bottom. All right. And then I'm going to rearrange the top to gather together the x's and the constants. But actually, maybe I don't need to write this as a fraction anymore. If you read it all the way across, it says 5x minus 16 equals this numerator, right? So at this point, I can multiply through the denominators, and the denominators just all go away. 5x minus 16 is what I started with, and then the resulting numerator, after rearranging a little bit, becomes a plus bx plus negative 2a minus 5b, like that. All right. And now we equate the like terms on either side. The coefficients on x are equal, so 5 equals a plus b. And the constant parts are equal. So negative 16 equals minus 2a minus 5b. Right. And now we solve the system by whatever means you like. I usually like doing substitution, so I'm going to take the first one, say b is 5 minus a, and then you plug that into the second one. This sometimes can be a pain to do, but it's not so bad. Negative 16 is negative 2a minus 5 times 5 minus a. And if we do the algebra here, minus 2a, this is minus 10 plus a. Add the 10 to the left side, it's negative 6, and on the right side is negative a. So a is 6. Is that right?
I got 3.
Yeah, on my paper it says, what did I do wrong?
You didn't just read the
Yes, I didn't distribute the 5, thanks. 10 plus 5a, like so, right? So this is minus, not minus a, it's, I think the minus 6 on the left side is okay. Negative 2a plus 5a is 3a. All right, great. So a is negative 2, is that right? Or should it be positive?
Positive. I have them both being positive, so. Isn't like when you distribute the 5 times 5, you get negative 2?
Oh yeah, what am I talking about? 5 times 5 is 25, not 10. I'm looking at the clock here. Sorry, I'm not doing so well. All right, let's go back. 5 times 5 is 25. All right, minus 25. Negative 5 times negative a is plus 5a, right? Add the 25 to the other side, I get 9 equals 3a. A equals 3. All right. I don't know if you pay attention to the videos that of our class, but sometimes random people watch them and they leave angry comments like you added the numbers wrong or something. Yeah, it's true. They're not so angry. All right. A is 3. Be kind online. You never know who's going to read your comments. That means B, so going back here, B is 5 minus A, so B is 5 minus 3, which is 2. All right, I think this is correct. At least that matches what it says on my paper. Okay, the whole purpose of this is being able to do the integral, remember? So that means my original integral, which said 5x minus 16 over x squared minus 7x plus 10. The whole point of doing all of that stuff was so that I can rewrite what's on the inside as the partial fractions, where we determined the a was 3, so that was the first numerator, and the make sure you get the denominators in the proper order. I had x minus 5 under the a. So this is 3 over x minus 5, and then plus 2 over x minus 2. And then finally we do the integral each time. Those fractions each become natural log of that denominator. And the numerators end up just as coefficients in front. So this is 3 natural log x minus 5 plus 2 natural log absolute value x minus 2. There you go. All right. This is the partial fractions trick. I got one for you all to try. Hopefully you're feeling better than I am at this point. It's not really that late in the day, is it? But what do we got? Oh, here it is. All right, this one is going to be very similar. Let's try integral 4x minus 1 over x squared minus 3x minus 4. See how you like it. Leave the integral for a while and just do the partial fractions and then come back to the integral at the end. By all means, chat with your friends about it. I'm going to start writing what I have up here. Can we talk about this one? It looks like people are doing okay. I don't know if everyone's finished, but that's all right. This is my common denominator. Then I can distribute on the top and recombine everything. I think I don't really need to keep track of the denominators anymore. What I start with on the left is 4x plus 1, and it should equal ax plus a plus bx minus 4a, right? And then rearranging things, 4x minus 1 is going to be a plus bx plus a minus 4a.
4A or B?
4b. Yeah, I distributed the b here. Thanks. I had an inner monologue going right when she said that. I was thinking, I didn't screw it up yet, but I did. Even that thought was an error. All right. Equate the like coefficients. So it says 4 equals a plus b, and also minus 1 equals a minus 4b, right? That means solving the first one, it's going to say b is 4 minus a. When you're doing partial fractions, actually the first equation will always say a plus b equals something or other, so I'm always going to solve it in this way. B is 4 minus a, so this says minus 1 equals a minus 4 minus a. That is a minus 16 plus 4a. Huh? Is that right? I think so. Add the 16, I get 15 on that side. Add the a's, and I get 5a. So a is 3. And b being 4 minus a means b is 4 minus 3, which is 1. All right? So I go integral of whatever I started with, 4x minus 1 over that stuff, x squared minus 3x minus 4, is, doing the partial fractions, I get 3 over, make sure I get the right order, x minus 4 plus 1 over x minus plus 1 here, right? And then just do each of those integrals is a natural log of something. All right, great. This is how we do the partial fractions. We got 5 minutes. That's enough time to say a little something about some more complicated cases. But any question about the simple case, first of all? This is, I mean, it still takes you a few minutes to do it, but this is basically like the easy type of these partial fractions. It'll take you a few minutes, and you'll probably mess it up if you're me. But those are the most straightforward ones. What I want to talk about, there are actually a few variations that maybe you've done before if you did this in high school that I don't really want to get into, but I would like to discuss. So this works well with a quadratic on the bottom and a linear on the top. Linear meaning degree 1 polynomial divided by quadratic, right? It works well with a linear on top and a quadratic on the bottom. But this is, it's not clear how this is going to work if the top is not a linear. And the reason, like if the top was also a quadratic, for example, the reason that that's not going to work out nicely is because when you split apart the partial fractions, well, if the top is a quadratic, then you will expect to have 3 different coefficients on the top, but only 2 different of the partial fractions because the bottom is a quadratic and you factor it into 2 pieces. So some weird stuff will happen, I will just say. This is weird if the degree on top is more than 1. Right? If the degree on top is more than 1, then actually your partial fraction will need to have more than two coefficients to end up with to add up to the thing on top. But you're only going to get 2 because your quadratic in the denominator only splits into 2 parts. So there is a remedy for this, and this is another trick. So this is the trick to use in that situation is an old thing called polynomial long division. Some people, I kind of like polynomial long division. I know some people kind of hate it. This is also known as synthetic division, which is another way of doing the same process. And if you've learned either one, you may feel like the way that I'm writing it is weird because you learned to write it in a different way. It don't matter. You can write it however you like in your, however you want to write it. But anyway, let's just do real quick. We've only got a minute left. I'll do one here, and then we'll talk more about this next time. This one, we start with a cubic on top, but a nice factorable quadratic on the bottom. So I kind of like the bottom for the sake of partial fractions because it factors easily into a +4 and a -3. But the top is too crazy. The way to remedy this is by dividing. So we are going to divide that fraction. It is, and I'm going to write it as a long division. The denominator here dividing into the numerator like this. All right, this is the division that we're going to do. And you do this exactly like long dividing real numbers. I don't know if you actually remember how to long divide real numbers, but the idea is you look at the front here, which is x squared, and then you look at the thing you're dividing into, which is 2x cubed, and you say, how many times does this go into this? And the answer is 2x. You have to get used to doing this if you've never seen this before. That's because this thing times 2x would match that exactly. All right, so in this, you think of each term as like a digit of your long division. And in this digit, we need 2x to make that product match this exactly. The next step in long division is to multiply that thing up top by the thing to the left of the division sign. So I'm going to now multiply 2x times this business. I get 2x cubed plus 2x squared minus 24x. All right? I multiplied, distributed here, 2x onto each term. And then I wrote that down there. And then just like long division, I subtract right here. And if you did it right, the leftmost terms should cancel completely. If they don't, it means you put the wrong quotient up top. The next one, x squared minus 2x squared gives me negative x squared. The next one, negative 23 minus 24x. Make sure you do your minuses properly, but I believe that's plus x, right? And then finally, the 16 can drop down just like in a normal long division. All right, one more step. Sorry, I can see the clock says it's time to go. One more step. How do I, can anyone say what should I put here for my next term? You need a term up here, which when you multiply it here, makes it match exactly that. I would say -1, right? Here I have x squared. I want to match it with negative x squared. So what I have to do is -1. Multiply that through. It'll say minus x squared minus x plus 12. Subtract. Those cancel as they should. The next one, x minus negative x is 2x. The last one, 16 minus 12 is 4. All right? And the final long division is, so now we're done because the degree here is now less than the degree here. And it means that this original integral is the same as, remember what this whole long division means? The quotient, like this fraction, it actually equals 2x minus 1. With a remainder, and the remainder is that at the bottom, 2x plus 4 over x squared plus x minus 12. That's the remainder term. And what's the point of all that? The point of all that is here we can now do partial fractions because the numerator is now degree 1. All right, we'll finish that off next time and do some more examples like that. Thank you for your patience with my mistakes. Sorry about that.